and Dylan Maxwell, and their project called Three-electrode electrochemical cell with integrated pressure sensor.
Yeah, just share my screen.
Thank you, Dylan.
Okay. How's that look?
Yeah, we can see the screen.
Yep. Okay, great. Yeah, so here to talk about the progress that Liam and I have made on our project to try and design, fabricate, and test a three-electrode electrochemical cell with an integrated pressure sensor. So three-electrode cells are an important component in lithium-ion battery research. And so to first start, I'll go through the sort of main components of the lithium-ion battery. So the schematic here on the left. We have an anode on a copper current collector. Can you see the mouse? Let me get the pointer. Yeah, that's better. Yeah, we have an anode on a copper current collector, and then a cathode here on the right on an aluminium current collector, and that's separated by this membrane or separator, which with an electrolyte that allows the lithium ions to shuttle between the two sides of the battery. And so when we develop a new battery material, we typically test the material in two different configurations. So to begin with, we start with a half cell where we have the working electrode that we then test against a lithium metal electrode. So the lithium metal electrode acts as both a counter and reference electrode, because we have an excess of lithium metal, meaning that when we electrochemically cycle the half cell, the potential of the lithium metal doesn't change during the cycling, meaning that it can act as a reference electrode. So by measuring the potential difference across the two electrodes, the working electrode and the lithium metal, we can track the chemical changes and chemical reactions undergoing at the working electrode during the cycling. And then in a full cell, we then have, so this would be similar to how a battery looks like in your phone or laptop. We then have an anode and then a cathode, and we then use a potentiostat to measure the potential difference between the anode and cathode. But the problem there is then in a full cell, because the potential of the two materials are simultaneously changing, the potential difference gives us a measure of the the voltage between the two materials. But because both materials are changing, we can't track the chemical changes at each electrode separately. So what we can do is use a three-electrode cell by introducing a third reference electrode, which in a lithium-ion battery would be a lithium metal electrode. And then by measuring the potential difference between the anode and the reference electrode and the cathode and the reference electrode separately, we can then measure the voltage, or track the voltage changes, the potential changes of both electrodes separately. And this is important because then we can track the chemical changes in something that simulates more closely a full working battery. And also in terms of studying new materials, the battery degradation mechanisms are not always the same when testing in half cell and full cell regimes. And so in our project, we would like to integrate a pressure sensor into this with two main aims. So the first would be to try and improve the reproducibility of the experiments, because so when you put together these three electrode cells, you typically have a plunger or some kind of pressure plunger essentially to apply pressure between the anode and cathode. This is because stack pressure is quite important when assembling these cells. So because if the stack pressure between the anode and cathode is too low, then we can increase ohmic resistances, and if it's too high, then it may lower the battery performance. And the other thing we propose to do is to do some in situ monitoring. So I'll sort of go through this with an example of a material that has quite some interest in research at the moment, which is silicon. So silicon is expected to be the next anode material in next generation lithium-ion batteries, because it has 10 times, or can store 10 times more lithium than conventional anode materials, meaning we can increase the energy density. of lithium-ion batteries using this material. However, it's not without its issues. So when you lithiate silicon in the first cycle, it can expand by up to around 300%. And at the same time, at low voltages, we get this degradation of the electrolyte that forms this SCI layer, or solid electrolyte interphase layer, on the surface of the silicon. And then when we delithiate the material, the silicon then shrinks back to not quite its original size, but it shrinks. And then in subsequent cycles, when we relithiate the silicon, it then expands again. This SCI layer cracks and exposes fresh silicon surfaces, where more electrolyte then reacts and forms a new SCI layer. And over multiple cycles, we then get sort of this expansion and contraction that leads to, we get continuous SCI formation, and this leads to the eventual pulverization of the silicon particle, and then which leads to capacity fading and the eventual sort of failure of the battery. And so what we propose to do with the pressure sensing is, by monitoring this in situ, so during the electrochemical cycling, we can then relate the measurement back to the volume expansion in the silicon, and measure and sort of get an idea of the stress evolution within the silicon electrode, and then correlate that back to electrochemical data to give a deeper understanding of battery failure mechanisms. Yeah, so I'll pass over to Liam now to continue the presentation.
Okay, thanks, Dylan. So as Dylan was saying, 3-electrode cells are really valuable tools in examining electrochemical behavior. So other 3-electrode cell designs have been developed in the past. Notably, there's a type of cell that's referred to as a swage lock cell. So this uses the plungers that Dylan mentioned earlier. You can see them to the left and right of this image on the top left. Yeah, thanks. Dylan mentioned reproducibility, and in terms of applying a reproducible amount of pressure when testing different cells. In this type of design, the two plungers are effectively tightened in opposition to each other, so it's quite difficult to control the amount of pressure that's applied to the cell. So the reference electrode in this design is introduced in the middle through a kind of probe-like wire, and it has a small piece of lithium attached to the end at a fixed distance from the rest of the cell, which is being tested. So the things that we'd like to change and improve on this design are trying to make it as easy as possible to assemble within the glove box, and specifically also trying to introduce the use of standard components that we have inside the glove box, and in particular, so using a piece of lithium as the reference electrode. One of the things that we would like to try with our design is, at the moment, at the end of the probe, like reference electrode, there's a small piece of lithium. If we could use a larger 14mm standard lithium chip, that would also provide a larger surface area, which would hopefully make the behavior closer to the ideal constant potential that Dylan mentioned earlier. So by changing the order of the components, it would also hopefully inherently make it easier to control the important difference, the key distance between the working electrode and the reference electrode. So in terms of making it easier to assemble inside the glove box, we've also changed the overall design of the cell as well. Can I have the next slide, please?
Yeah.
Thanks. So in the design that we're proposing, instead of adjusting the two plungers or the two electrode contacts in opposition to each other, we have a kind of vertical design. So we have two interchangeable electrode contacts to make it easier to manage the components inside the glove box. And we have the sensor down at the bottom of the cylinder. So the way that this is assembled is shown by this 3D view on the right. So yeah, if you could click once, please, thanks. So in assembling the cell, the first electrode contact would be inserted through the top, and then the cell stack components that you can see in the top left would be inserted on top of this contact, and then the next electrode contact applied on the top of that. So we have the seal that is provided by the two O-rings that you can see in green in the exploded diagram on the left. So to adjust the pressure that's applied after assembling the cell, sorry if you could just click it again. So the pressure sensor position would be at the bottom of the cell, and the contact by the electrode contact to the pressure sensor is through this hole at the bottom. So after assembling the cell, the cap that's at the very top of the exploded view can then be adjusted, and we can control and monitor the amount of pressure that's being applied to the electrode stack, so that the results are more reproducible, in addition to using the sensor to measure the changes in pressure as the cell is cycled. Yeah, can I have the next slide, please? Thanks. So obviously, like everybody else, our access to the labs has been quite limited. So far, the progress that we've made is we have the designs that you've seen on the previous slides, and they've been 3D printed in ABS to check that it's ergonomically easy to handle inside the glove box, and check that the components fit together. So the next step is to manufacture the effectively the final casing with proper seals for the electrode contacts and so on, and that will be manufactured from PEEK and stainless steel. After that, we then need to demonstrate that the electrochemical results that we get from this cell are comparable to those from either existing three-electrode designs or from well-characterized electrode materials, to demonstrate that the cell is functioning as an electrochemical system. And then the next stage is to integrate the pressure sensor. So far, we've used a very cheap pressure sensor. It's effectively the same Wheatstone bridge electronic setup, and looked at ways to calibrate that type of pressure sensor. In terms of how we would use that inside the cell, it may be possible to look at kind of semi-quantitative changes in terms of like the starting and final pressure for a certain cell, or comparing the change in pressure for different cell designs. Yeah, so that's as far as we've got so far, and hopefully we'll be able to update you with some more results and outputs later in the year.
Thank you. So thank you very much, Liam and Dylan. I believe this is time for questions.
Yeah. Any questions? Welcome.
And yeah, anyone would like to ask any questions, please? Actually, I have a question about the pressure sensor. Is it supposed to measure the pressure or to regulate the pressure in the system?
So it's supposed to measure the pressure. In the initial stages of setting up, we can also use it to gauge how much pressure we're applying to the system. So I
have a question, if I may ask. What is the unique benefit of your pressure sensor compared to the state-of-the-art pressure sensors?
So at the moment, there are 3 electrode cells available, but they don't have pressure sensors integrated into them. Although you can, I guess, measure the pressure due to the expansion of the electrode materials, it's not I don't know, Dylan, you can speak more about this.
Yeah, no, yeah. As far as I know, I've never seen a three-electrode cell with a integrated pressure sensor.
Right.
So,
okay. So that's the thing. So it's integrated within the electric cell.
yeah, exactly. Yeah.
Okay.
And also, I could add some comment because in the three-electrode sensors, we are possible to get a more reliable result because commercially the battery only have 2 electrodes. So actually, the voltage or some electrochemical information what you got maybe not that reliable. So if we add a reference electrode, it gives us more reliable results for the understanding.
Yeah, exactly.
Thank you. Any more questions, please? If not, we would like to thank the speakers. Thank you, Liam. Thank you, Dylan. And we are looking forward to your final presentation in June.